Hello everyone. Now I'm going to present my smart door lock system. For the outline of my presentation, we have the introduction where I explain about the microcontroller that was used in this project, and we also have a project introduction where I introduce the main project, the components used to build it and its functions. We also have project process where I explain a step-by-step of creating this project. We also have the main code or code breakdown where we analyze the code detailedly. And last, we have the conclusion where I summarize the presentation and also the project. For introduction, we use a Lolin D32 microcontroller base where it is a powerful dual core processing which has a built-in Wi-Fi and Bluetooth capabilities. It has also a versatile hardware features such as extensive GPIO pins for sensor, actuator, and peripheral interfacing. It also has a compact form factor ideal for prototyping and IoT applications. It is also a Arduino IDE compatibility. It supports familiar programming environment for seamless development and also appeals to both hobbyists and professionals for innovative IoT solutions. For the project introduction, this code implements a smart door locking system using Lolin D32 development board. The system utilizes an ESP32 microcontroller and integrates various components such as SparkFan, APDS9960, which is our color sensor, and a servo motor. The primary function of this project is to assess the door lock by analyzing the color scan using the color sensor. The Lolin D32 connects to a Wi-Fi network, allowing it to send notifications via IFTT based if the door is locked or unlocked. The servo motor serves as a simulated door lock, providing a visual representation. This is the project diagram. For the components used, we have Lolin D32, which serves as a main controller for the project, facilitating connectivity and processing tasks. We also have a micro servo motor, which acts as a visual indicator for the door status, simulating a door lock mechanism by turning to a specified angle based on the color classification. We also have APDS9960 color sensor, which employed to capture the ambient and RGB light values, enabling the system to analyze the color of the key scan. And lastly, we have the IFTTT integration, where it sends notifications, providing a seamless way to alert users about the status of the door. For the project process, in this area, I'm going to tell you a step-by-step process on how I do my project. First, we have this data gathering, where we use APDS, our color sensor, to scan two colors to simulate the door status. And next, we have the data training, where we train the data that we gathered to a neural network to know what type of color is scanned. And after that, we also need to test the data for us to know if the neural network can identify the color accurately. And lastly, if we all did the testing, the training, and the gathering, and we're satisfied, we can now execute the project. For the first step, we have data gathering. For data gathering, I use Tolin D32 and our color sensor to scan green and red colors that serve as the data sources, which represents cards passes that will scan to determine the door status. The data collection process involves scanning each of these colors 50 times using our color sensor. Subsequently, after completing 50 scans for each color, a set of data is generated for analysis. This is the data gathering code. This code is for a color classification system using a Lolin D32 and our color sensor. It collects data on ambient light, red, green, and blue light ratios when an object is closed. The goal is to distinguish between green and red colors, representing different color status, and the LED indicates the data collection. And after gathering 50 sets for each color, the code exports the feature data for training. After that, you can copy the feature data for later use. This is how I gathered my data. First is we have two colors, which is red and green, and we need to scan it using our color sensor 50 times each. Just like this. Just put the green card on top of the color sensor and let it scan for 50 times. After that one, we can scan again the red color. After we scan those colors, a code will be exports the feature data for training, which are these two. We have the first file, which is the green.txt, which includes the data of the green card. And next one, we have the red.txt, where it includes the data for the red card. Next is the data training. After collecting the data, the next step is to initiate the training process. Initially, we load the two datasets, which are green.txt and red.txt. Once loaded into the code, we proceed with the training. During this phase, the objective is to achieve a low loss, indicating higher accuracy in predictions. If the obtained loss is very high, we can do the training process a lot of times just to improve the results. Following the training process, the mean is computed, and the subsequent step involving copying and pasting this mean into a file named doorlock.txt, and we're going to convert it to a JSON format, resulting in a file name doorlock.json. This Arduino code establishes a colors classification system using a neural network and an APDS 9960 to collect RGB color ratio data. The setup initializes necessary libraries, configures the sensor, and pre-processes the training data for model training. The neural network model, consisting of input, hidden, and output layers, is constructed and trained on a dataset using mean squared error loss and Adam optimizer. In the loop, the sensor continuously reads colors data, and if an object is close enough, it calculates color ratios, pre-processes the data, and feeds into the trained model for prediction. And next, we have the data testing. After obtaining the mean of the trained data, we proceed to test its accuracy in classifying green and red colors. Within the data training code, specifically in the final section of the void loop, a testing mechanism has been incorporated. The code dictates that if the predict val or the predict value is greater than 0.5, then the classification is considered as green. Otherwise, it is classified as red. Therefore, when scanning for green, the output should be printed as green in the serial monitor, and when scanning for red, the output must be red in the serial monitor. This is how I test the data that we gathered. First, we need also the two colors, and we need to scan it on our color sensor. If we scan the green card, it should print in the serial monitor a text of green, and if we scan the red color on the color sensor, it should print in the serial monitor red, just like this one. When we scan the green color, it will pop up green, and if we scan the red color, it should pop up red. And for the last process is our project execution. After gathering, training, and testing our data, we proceed to execute the project using the following components. We use Lolin D32, our color sensor, microprocessor, and IFTTT. Once the components are connected to their designated pins, we load the doorlock.json file into the code. Uploading the sketch enables the code to read the file, and upon running the code, the serial monitor displays door opening while line shows the door is unlocked, and vice versa. Beyond the outputs, the code also controls a microservo motor to function as a lock. If the color sensor detects red, indicating that the door is locked, the motor turns 90 degrees. But if it detects green, the motor will turn 0 degrees, signifying that the lock is disengaged. This is the simulation for the project execution. For this one, we need to scan the color green. And once we scan the color green, the servo motor should rotate 0 degree and there's a notification that will send on the line. See this one. As we scan the green card, there's a notification in our line saying that the door is unlocked. And in our serial monitor, there's a print of text including door opening and notifying unlock. But if we scan the color red, the servo motor will turn 90 degrees and there's a notification in our line saying that the door is locked, and also in the serial monitor there's a text of door closing and notifying lock. This is the project execution video. As you can see, once I scan the red color, there's a notification on my line saying the door is locked, and also there's a print in serial monitor. See that one, door closing or lock, and when you scan the green color, it says that the door is unlocked, and in the serial monitor, it says that the door is opening and notifying unlock. Now I'm going to explain to you the different parts or the most important parts of the code of the main code. First is we have the include statements. These lines includes necessary libraries for neural network models such as flag model, wire, APDS 9960, Wi-Fi, ESP32 servo, and HTTP client. Next is defined statements, where the constants are defined just like the Wi-Fi credentials, IFTT URL, and servo motor positions for locked and unlocked. For the third one, you have the global variables, where are instances of the servo class, a neural network model, flag model, and our gesture sensor, which is the color sensor, are declared. Additionally, some global variables for timing and door state are also defined here. Next one, we have our notify function. This function sends a notification using the IFTTT service based on the door's status, if it's locked or unlocked. Next is we have the setup function, where it initializes the serial communication, servo motors, sensors, Wi-Fi, and the neural network model. And the last one, we have the loop function, where it provides the Arduino code manages the real-time prediction and control logic for a smart door system. It continuously monitors a proximity sensor, and when an object is detected in close proximity, wherein the proximity value is equals to 255, the built-in LED is turned on. The code then reads ambient light and RGB values, where it calculates the color ratios and pre-processes the sensor data for input into a serial neural network model, which will be trained for the color classification. The model predicts whether the detected object is a green or red. Based on this prediction, the system takes actions such as controlling a servo motor to simulate the opening or closing of the door and sending notifications through IFTTT. Additionally, it performs auxiliary tasks such as controlling external IDDs and introducing delays for timing purposes. The system resets certain variables after each detection cycle, allowing it to continuously scan for new objects and make real-time predictions. Overall, the code orchestrates the integration of sensor readings, machine learning predictions, and actuation to create an intelligent smart door lock system. And for the conclusion, the provided Arduino code constitutes a comprehensive implementation of a real-time door lock system. Leveraging the ESP32 microcontroller, the system integrates various components including APDS 9960 proximity sensor, servo motor for door simulation, and flag model neural network model for color prediction. The code orchestrates a continuous loop where it monitors proximity, reads RGB and ambient light values, pre-processes data, and utilizes the machine learning model to classify the colors of the card. The system dynamically responds by activating a servo motor to simulate door opening or closing and send notification through IFTTT warranty accordingly. The implementation showcases the seamless integration of sensor data, machine learning predictions, and actuation, providing a versatile and intelligent solution for a smart door lock system. That's all. Thank you for listening.